Let us provide a closure to this topic by analyzing this problem in some detail. The problem was that we had to do a 2 to the power of 3 design. That means we had to conduct 8 experiments involving 3 factors at 2 levels each. But then the 8 experiments could be done by 4 people doing 2 experiments each. And the 4 people could have skill levels of varying levels. And therefore, we do not want the skill level to influence the outcomes of the experiment very much. So the question is, what would be a good way to assign the 8 experiments into 4 blocks of 2 experiments each, with each block representing a person with a certain skill level doing that. So we had put up 2 choices for this situation. We had these 2 choices, which is denoted in the left and in the right. So in each case, we have used 4 different colors in that stands for the 4 different people or for the 4 blocks. In the assignment shown on the left side, we have experiments 1 and 7 in one block, experiments 2 and 8 in another block, experiments 3 and 5 in the third block, and experiments 4 and 6 in the fourth block. That means this experiment 1 and 7 goes to scientist 1. This experiment 2 and 8 goes to scientist 2 or chemist 2. The experiments 3 and 5 in this table go to scientist 3, and experiments 4 and 6 goes to scientist 4. This is the assignment. So we're asking the question, is this okay, or does it have some fundamental flaws? As opposed to the experiment that you see on the right hand side, where experiments 1 and 8 will be done by one of the scientists, experiments 2 and 7 will be done by another scientist, experiments 3 and 6 would be assigned to the third scientist, and experiments 4 and 5 will be assigned to the fourth scientist or chemist. So amongst these two designs, which one is better? And in fact, that leads to the open question of, is there a better design than the best of these two designs? So that is something that one can explore. But let's just focus on these two. Now, for a minute, just freeze this video and take a look at these two experimental designs or the assignments and try to see which assignment, either the one on the left or the one on the right, which one is better. Jot down your reasons. I hope you have indulged in that exercise of trying to find out or trying to kind of recommend the better of these two designs. Let's look into the solution that I have in these slides. Now, let's analyze experimental design 1 first. As already stated, experiments 1 and 7 constitutes first block or block 1. The color used here is yellow, and the first block means we say it belongs to or it is assigned to scientist 1. Experiments 2 and 8 form the second block, assigned green color, and those two experiments are assigned to scientist 2, and so on. As you can see there, for experiments 3 and 5, that constitutes block 3 and shown in purple color, and experiments 4 and 6 shown in blue color forms the fourth block. So this is the proposed assignment, and the question is, we'll analyze whether it's a good assignment or not. So let's take a first glance at it. If you look at column C, let's say we take a very naive approach, we take column C, and then you find -1, right, is assigned to all of these 4 colors. For example, if you take C is equal to -1, it is assigned to all of the 4 colors. That means every scientist gets to do one experiment with C is equal to -1 and one experiment at C is equal to +1. This is the observation we make. If you take factor B, right, or X2 as you might call it, if you take a look at the -1s, right, you can see all the 4 colors being represented for -1. So this one is yellow, this one is green, this one is purple, this one is blue. So uh, each of the scientist or the chemist gets to do experiments with B set at -1 and an experiment where B is going to be equal to +1, as you can see here. So purple, blue, yellow, and green. So each scientist gets to do one experiment where B is equal to -1 and one experiment where B is equal to +1. If you come to factor A, if you look at the -1s, the -1s are yellow, purple, purple, and yellow. So you see there's a difference between what we observed for columns B and C. There is something different when we analyze factor A. That means the low settings for factor A is either assigned to the yellow block or to the purple block. That means it is either in block 1 or block 3, and settings for A is equal to +1 is assigned to the green and blue blocks only. That means the second and the fourth block. So some scientists get to do experiments only when A is equal to -1, and the remaining scientists get to do the experiments when A is equal to +1. So it is not evenly distributed amongst all the four scientists, right? That means each of the four scientists does not get to do an experiment where A is equal to +1 and an experiment where A is equal to -1. All right. So there is this important difference. So when we look at column A, in very simple terms, we can say column C -1 has got all the four colors, which means all the four skill levels are assigned to an experiment where C is equal to -1, and the same goes for C is equal to +1. Shows all the four colors. So the conclusion in our language is that the direct effect of C will not be confounded or contaminated by the blocking. That means the skill level will not influence the effect we would calculate for factor C. Same for column B, right? -1 has all the four colors and +1 has got all the four colors, which means -1 is handled by scientists with all skill levels. +1 for factor B is handled by all scientists with different skill levels. So the direct effect of B that we estimate from the collected data will not be confounded by the skill level of the scientists that are conducting those experiments. When it comes to column A, -1 has only two colors and +1 has two colors. Specifically, -1 has yellow and purple, while +1 has green and blue. That means people of two skill levels get to do experiments where A is equal to -1, and people of the other two skill levels get to do experiments with A is equal to +1. So the direct effect of A will be contaminated or confounded by the skill level of the chemists who are conducting the experiments, right? And this is a danger when a direct effect is confounded with some factor that is not very good, because we believe that the direct effects are going to be significant. So since direct effect of A is confounded with the skill level of the scientist, this blocking arrangement is not good. This blocking or this assignment of four blocks will not be enough to minimize the effect of the confounding factor, which in this case happens to be the skill level of people. So if you take a wider look at experimental design 1, what you see is, if you complete the table by introducing columns A, B, AC, BC, and ABC, right? The three-factor interaction and let's say the two-factor interactions that are possible in the system, you can see if you look through this data carefully, yellow block is assigned if ABC is equal to -1 and BC is equal to +1. So look at it, ABC is equal to -1 and BC is equal to +1. You are assigned the yellow block. That's the condition for something being assigned the um, yellow block. That means these are kind of the design generators. All right. So if you look at the green block, it is assigned in a way that means experiments are assigned to the green block if ABC is equal to +1 and BC is equal to 1. And this is important. So ABC should be +1 and BC is equal to +1. If these two conditions happen, then it is assigned the green block, as you can see. And for purple and blue, likewise you can see that, right? So there are four possible combinations of A, B, C and BC, right? ABC can take two values, could be -1 or +1. Likewise, BC can take two values, -1 or +1. If ABC and BC are both positive, then for that combination it is assigned the green block. If ABC is positive and BC is negative, then it is assigned the purple block. If both ABC and BC are negative, it is assigned the blue block. If ABC is negative and BC is positive, then it is assigned the yellow block. That is how this assignment has been made, right? Once you do this analysis, you can find that these are the rules. Okay, so just looking at the four possible combinations of A, B, C and BC, the experiments are assigned to the four blocks. But interestingly, what happens is these could be the basic generators, like ABC and BC could be the basic generators, but ABC and BC, if you multiply it, you're going to get a generalized generator. So if you take ABC and you take BC, so if you multiply these two, for example, ABC is negative, taking the yellow block, ABC is -1 and BC is equal to +1. If you multiply the two, -1 times 1 is going to give you -1. ABC multiplied by BC is going to give you A, B squared, C squared. Since B squared and C squared are both equal to 1, so ABC multiplied by BC will be equal to A. So when A is equal to -1, you're going to get yellow, right? So when A is, if you take these two, right? Again, ABC multiplied by BC will give you A, and A is going to be, in this case, for the green case, ABC is 1 and BC is equal to 1. So A will be ABC multiplied by BC, which is going to be 1 multiplied by 1, which is going to be +1. So A is equal to +1 gets assigned to green. Again, if you take the purple one, if you multiply the two, you will get A is equal to -1. So A is equal to -1 is assigned purple. And ABC is equal to -1 and BC is equal to -1. If you multiply the two, the left hand sides will give you A, B squared, C squared, which is equal to A. The right hand sides multiply to give -1 times -1, which is going to be +1. So these are the assignments to yellow, green, purple and blue. As you can see, when A is equal to -1, it can either be purple or yellow. When A is equal to +1, it will be assigned to green or blue, right? As you can see here, green or blue. Okay, so you can also say that from this result that the skill level is confounded with the direct effect. Because if I say B is equal to -1, it goes into all the four blocks, as you can see, right? If I say B is equal to -1, it could be yellow, it could be green, it could be purple, it could be blue. Likewise for B is equal to +1. Do the same thing for C, right? All the four colors will be there for -1, all the four colors will be there for +1. Do it for AB. So if you take AB, +1, yellow, blue, purple, green. So -1 is also green, purple, blue, yellow, all the four colors. You can do it for column AC as well. So B is clean, C is clean, AB is clean, and AC is clean. That means those four things, the direct effects B and C, and the two-factor interaction effects AB and AC, are not confounded with the skill level of the scientists who are doing the experiment. However, when you look at BC or ABC or A, you will find it is very different from the other four columns. That means these three things are confounded. Effect for A, effect for BC, effect for ABC are all confounded with the skill level of the operators or the scientists in this particular design. So you will never be able to say this is the effect of factor A clearly, because a part of that may be due to the result of the different skill levels amongst the scientists who are conducting this experiment. Same goes for BC, same goes for ABC. So whatever I described earlier is depicted in this particular slide. So I took for LO, I took this and this, these were the conditions, and then I multiplied the two to get A is equal to -1. So A is equal to -1 will be assigned yellow, A is equal to -1 will be assigned purple, and A is equal to +1 will be assigned either blue or green. This shows that the direct effect A becomes involved in block assignment because it is not spread amongst all the four blocks. A is equal to -1 is not spread amongst all the four blocks. A is equal to +1 is not spread amongst the four blocks. A is equal to -1 is concentrated on two blocks. A is equal to +1 is concentrated in two other blocks. Therefore, it can become a very significant confounding factor when we try to assess the effect of factor A from the experimental data that we collect. If you look at it carefully, if I say -1 for B, it will be in all the four blocks. Similarly, C is equal to +1 means you will find that all four blocks do an experiment where C is +1. But if I say A is equal to -1, you would say it has to be either a purple block or an yellow block. It is not going to be in green or blue, right? So this is another way of looking at it. Let us now look at computing the effect of A as we normally do. So I have taken the experimental design 1, the same colors are assigned for the blocks and the same experiments are also assigned to the blocks, so everything is intact, and I've just added this label here, right? The way we label, when everything is low we label it as bracket 1, when everything is high it is labeled as ABC, when A and C are +1 and B is -1 we label it as AC, etc. Right? So this is the usual labeling process. So the effect of A is obtained by taking all the experiments where A is +1, computing the average of those four measurements, and taking the average of all runs with A at its low value. So you take experiment 1, A is low, experiment B where A is low, experiment C where A is low, and experiment BC where A is low. So you take all those four readings of the output and then you average it out to get this, right? So, and you subtract the two averages that you have computed, you will get the effect of A, right? Effect of factor A is obtained in that particular manner. Now, so this is the mathematical expression for that. And then you can rearrange it in this particular form. And now instead of kind of using the labels, we are replacing it by blocks now to understand that a bit more. So this is correct. All right, this is how we compute the direct effect of A. But now let's replace the labels by the blocks. So A is green, right? A is green and AB is blue and so on, right? So we do that. Then what you see is you see green plus green. So you do not see green minus green, which is important for the effects of the skill level to cancel out. So you see green adding to a green and blue adding to a blue and yellow adding to an yellow in some sense, because you can say it as minus yellow plus yellow. The yellow plus yellow can be inside the brackets. So it's minus yellow or minus purple minus purple. It is not like where one of them has a positive sign and one of them have a negative sign. So we do not have the cancelling patterns, which means the main effect will be confounded with the blocking that has been assigned. This is a serious design flaw. If you do the same calculation for B, C, or you do it for, as we did before, if you do it for AB and AC, you would not see this problem. You would see green minus green, blue minus blue, yellow minus yellow, purple minus purple, that will appear. But for factor A effect and for ABC effect and for BC effect, you will see you will get green plus green, blue plus blue, or minus green minus green, things like that. It will not cancel out. Okay, so this experimental design 1 is flawed. We would not take up this assignment, right? Because it is going to result in a lot of ambiguity in interpreting the results. So in a nutshell, we can represent this as follows. So we know that ABC and BC were used as the blocking factors, right, in coming up with the assignments. So factor BC and factor ABC are denoted as blocking factors 1 and blocking factors 2 respectively, right? Remember, here we used ABC and BC as the basic blocking factors, deciding which block an experiment should go. These two variables played a role. That is how this design came up. And therefore, we call this B1 and B2, or we can also call it BF1 and BF2, blocking factor 1 and blocking factor 2, or simply B1 and B2. All right. Now, we also know that these two blocking factors will multiply and give us a new blocking factor or a derived blocking factor, which in this case would be equal to A. So these are the starting blocking factors. We need that because we have to get 4 people to do the experiments. That means we have to do 4 blocks, and therefore for 4 blocks means 2 to the power of 2. Therefore we need 2 basic blocking factors, and we chose BC and ABC for that role. But these two interact and multiply to give you this blocking factor 3, right? Which in this case happens to be ABC multiplied by BC, which is equal to A. So if you look at these things, you will see that um, if you have ABC is equal to -1 and BC is equal to +1, you are assigned block 1, and that corresponds to experiments 1 and 7 in our list. That block comprising of experiments 1 and 7 also happen to have A to be assigned as equal to -1. All right, so that is what it is. Now, if ABC is equal to +1 and BC is equal to +1, it is going to be in block 2, and experiments 2 and 8 fall in that category. And we also see that for those 2 experiments in block 2, A has a value of +1. Likewise, when ABC is equal to +1 and BC is equal to -1, experiments 3 and 5 in our table, they are assigned block 3, the blue block, for example, in this particular table. And for the experiments in block 3 here, AB has got a -1 value, right? The setting is -1 for factor A in those things. All right. And likewise, you can analyze 4th block, which comprises of experiments 4 and 6. And in this particular case, both A, B, C and BC have low values, that is -1 for both of them, leads to A is equal to +1. All right. So experiments 4 and 6 will have A is equal to +1, whereas BC and ABC will have -1 for them. So this is the assignment. It is a poor assignment because the skill levels or the blocks will confound with the direct effect of A. Now, if you look at the experimental design 2, in the first glance, you see that let's start from C. You know, for C is equal to -1, we have all the four colors: purple, orange, green, and blue. For C is equal to +1, we have all the four colors. That means each of the four blocks will have one experiment with C is equal to -1 and one experiment with C is equal to +1. If you do it for B, B is equal to -1 corresponds to purple, orange, blue, and green. And B is equal to +1 corresponds to green, blue, orange, and purple. All the four colors are represented for B is equal to -1 and for B is equal to +1. That means each of the four blocks will contain one experiment with B is equal to -1 and one experiment with B is equal to +1. So the skill level will not be confounded with factor B as well. Like it was not confounded with factor C, this is also good. Now A was a problem in our first design. Now let's look in the second design what is with A. So if you take A -1, purple, green, blue, and orange, looks great. And A is equal to +1, orange, blue, green, and purple. So each of the four blocks has one experiment with A is equal to -1 and one experiment with A is equal to +1. So the skill level will not confound with the direct effect of factor A as well. So all the direct effects A, B, and C are clear from the entanglement with the skill level of the scientists who are doing this experiment. So this appears to be a better design, right? So if you take a look at the A column now, A is equal to -1 has all the four colors. That means all the four skill levels are assigned A is equal to -1. Again, all the scientists with the different skill levels are assigned an experiment with A is equal to +1. Same happens for B, same happens for C. All right. So, and if you do the computation of the main effect for A, if you write that equation like we wrote here for design 1, if you do it for design 2, which is featured here, you will see that it will have this pattern. When you write out that equation, you will see there will be a yellow minus yellow, there will be a blue minus blue, there will be a green minus green, and there will be a purple minus purple. That means the biases introduced by people with different skill levels will all cancel out, right? So that is the nice thing about this design. So this is the conclusion from our just analysis here. You can also do this calculation for B and C and convince yourself that there is no confounding of the direct effects by this block assignment. If you complete the table, you will see the table to be like this. So please do this and convince yourself that this is the full table. And if you look at the rules for the different blocks, if you take purple block, you would see that when AC is equal to 1 and BC is equal to 1. So AC is equal to 1 and BC is equal to 1 gives you the purple block. So we can take AC and BC as the basic, the block factors. Block factor 1, we can even call it B1, but let's say we call this as block factor 1 and BC as block factor 2, right? So AC can take two values, -1 plus 1. BC can take two values, -1 and +1. All right. So there will be four combinations of AC and BC. So if AC and BC are both equal to +1, it is purple. And we can call purple as block 1 if you like. If AC is equal to -1 and BC is equal to -1, what happens is you get blue, right? When AC is equal to -1 and BC is equal to -1. So you get blue. And when AC is equal to +1 and BC is equal to -1. So AC is equal to +1 and BC is equal to -1. You're going to get green. Look at the other green as well. AC is equal to +1 and BC is equal to -1. You get green. And then when AC is equal to -1 and BC is equal to +1, it shows it is going to be orange color. So these are the basis on which the experiments are assigned to the 4 blocks by looking at the value of AC and BC. Now, interestingly, AC and BC will interact, right, to give you the third derived blocking factor, right? So AC multiplied by BC will be ACBC, which is going to be ABC squared, which is going to be equal to AB. So what happens is this is going to be BF3. This is the derived quantity. So this is going to be 1. This is going to be 1 again. All right. This is going to be -1 and this is going to be -1. So what it says is if AB is equal to +1, it is going to be either purple or it's going to be blue. If AB is equal to -1, it is going to be either green or orange. In the same way that if you said AC is equal to +1, it could be purple or green. And AC is equal to -1, it could be blue or orange. Not all the 4 colors are represented. This is the most important thing. My AC is equal to 1 leads either to purple or green. Not all the 4 colors. AC is equal to -1 leads to blue or orange. Not all the 4 colors. All right. This is in contrast to what you notice for A or B or C or for ABC. So these two-factor interaction terms get confounded with the skill level. At least we save the direct effects from being confounded. All right. So I hope you understand this analysis. So you can take B1 and B2 to be the basic blocking factors, and from AB and AC you can get BC to be the third factor. So in any case, B1, B2, B3, right? Like I said here, you will have those 3 things, AB, AC and BC. You can take any 2 as the starting and then you can derive the third one. So in any case, you see that B1, B2 and B3 are the 3 blocking factors that decide. Any 2 of them would decide which block the experiment goes to, but all the 3 will be confounded. All these 3 will be confounded by the skill level of the operators. So these interactions are confounded, as you can see here. So if you take AB, let's say here B1 and B2 are the basic blocking factors, and B3, let's say, is the derived one, right? So you take these 2, you multiply, you get BC. So if you take BC is equal to +1, it will either be in the green block or in the blue block. Okay. And if you take BC is equal to -1, it will either be in the other 2 blocks, right? The colors are different here. This you can call as somewhat of a gray, and this is of a different kind of blue, but only 2 blocks are represented. So for these 3 factors we have this problem. But if you take factor A, if it is -1, it is in all the blocks. If it is in +1, it is in all the blocks. So the factor A, the effect will not be confounded with the skill level of the experimenters. Even if you take ABC, ABC is equal to -1, features in all the 4 blocks. and ABC is equal to plus 1 features in all the 4 blocks. So you will see that pattern of green minus green, blue minus blue, etc. for ABC. So ABC is not confounded in this case. All right. So the direct effects and the 3-factor interaction is not confounded with the skill level of the operators. So let us now gather some observations from whatever little we did. When we had to assign experiments into 2 blocks, all we needed was one blocking factor, and only that factor was confounded with the, for example, the skill level of the operators, right? So you can say that only that factor which we pick as the blocking factor, only that was confounded with the blocks. And the choice was easy. We could choose the blocking factor to be the highest interaction term. Either base it on AB if it is a 2-factor experiment. If it is a 3-factor experiment, base it on ABC. If it is a 4-factor experiment, base it on ABCD, because these would be the highest interactions in those systems. And that would be the only interaction that will be confounded with the blocks. So it was easy. Then we went to a slightly complex situation where we wanted to have 4 blocks. That means if you had a 2 to the power of k design, we had to split it into 4 blocks. That means 2 to the power of 2 blocks, and each block would contain 2 to the power of k minus 2 experiments. So when k was equal to 3, that means 8 experiments overall, and we wanted to do it in 2 blocks. When k is equal to 3, we have 8 experiments, 2 to the power of 3. We wanted it in 4 blocks, therefore that is 2 to the power of 2. So this is the number of blocks represented as 2 to the power of something. This would be the number of experiments that will be assigned to each block. So when k is equal to 3, 2 to the power of 3 minus 2, which is equal to 2. So you had 2 experiments in each block. Makes sense, right? 4 blocks, 2 experiments in each block, giving a total of 8 experiments. So because we had 2 to the power of 2 blocks, we should have 2 blocking factors. So this is the key thing here. 2 blocking factors. So this matches with that. But the 2 blocking factors will generate a third blocking factor, because you can take the 2 blocking factors and you can multiply them to get a third one. So think of a situation where we have to assign experiments into 8 blocks. Let's say we are planning a 2 to the power of 6 design, which means 64 experiments, and you have to assign it to 8 scientists. So into 8 blocks, and therefore each block will have 8 experiments. All right. So in that situation, if you have to have 8 blocks, that means 2 to the power of 3 blocks, you should have 3 blocking factors, basic ones. And then the 3 will interact 2 at a time, and all the 3 together to generate other blocking factors. All right, so the situation gets really interesting. But just sticking to this, doing it in 4 blocks, the 2 basic blocking functions or blocking factors will generate a third one. For example, ABC and BC will generate A, which to be the third blocking factor. So this was in design 1. ABC and BC were the 2 basic blocking factors, and that generates the third one, which is going to be ABC multiplied by BC, which is equal to A. In the second design, AB and BC were chosen as the basic blocking factors, and AB and BC interact to generate AC. So this clearly shows design 1, because this is the third blocking factor, the direct effect will be confounded with the skill level of the operators. In this particular case, you have only two-factor interaction terms that will be confounded. All right. So overall, there will be three interactions that will be confounded with the blocks. Okay. So in the first case, if you went with design one, so these are the three interactions: A, B, C, B, C, and A. These three interactions, so to say, will be confounded with the skill levels, or will be confounded with the blocks, because the blocks are based on the skill levels in our example. So that is the case. In design 2, these three factors will be confounded with the blocks, right? And basically the idea is to not have the direct effects to get confounded with the blocks. That would be a really bad design. So try to push the confounding with as higher order interactions as possible. Make sure it does not confound the direct effects. If possible, make sure it doesn't even confound with the two-factor interactions and so on. But sometimes that may be difficult to achieve. So try to preserve the direct effects to not get confounded with the blocks. So the number of basic blocking factors will be equal to the logarithm to the base 2 of the number of blocks. So if you wanted 4 blocks, it will be log 2 of 4, and you can write this as log 2 to the power of 2, which will be 2. So you'll have 2 basic blocking factors. So if you want to have 2 blocks, so log 2 of 2, which is going to be equal to 1. So you have 1 blocking factor. If you want to have 8 blocks, then the number of basic blocking factors will be log to the base 2, 8, which is going to be log 2 to the power of 3, which will be equal to 3. So you have to start with 3 basic blocking factors, and those 3 will interact, right? So if you had BF1, BF2, and BF3 to be the 3 basic blocking factors, because we wanted 8 blocks. Now BF1 and BF2 will generate a new blocking factor. BF1 and BF3 together will generate another blocking factor. BF2 and BF3 will generate another blocking factor, and BF1, BF2, BF3 together will have another blocking factor. So you will have the basic 3 plus the derived 4. So you will have 7, right, interactions that will be confounded with the blocks, and that is what this says. So when the number of blocks is 8, 8 minus 1 will be the number of interactions that confound with the blocks, as we showed here. BF1 is one factor, BF2 is another factor, BF3 is another factor. BF1 and BF2 interact to give the fourth factor. BF1 and BF3 interact to give the fifth factor. BF2 and BF3 interact to give the sixth factor. BF1, BF2, and BF3 together will interact to give the seventh factor. So when the number of blocks is 8, then the number of interactions that will be confounded with the blocks will be 8 minus 1, which is equal to 7. So if the number of blocks is equal to 4, as we analyzed in this particular video, the number of interactions that will be confounded with the blocks will be 3. Which 3? It's your choice. Therefore, we have to do that wisely. In design 1, the 3 interactions were A, B, C, B, C, and A. In design 2, it was A, B, B, C, and AC. So in both cases, it was 3 factors or 3 interactions that confounded with the blocks. But this is better than this, right? So the circled one is better. So this slide basically tells in detail if we wanted 8 blocks, right? So we will have 7 factors that will be confounded with the blocks. So if I choose, right, AB, AC, and AD as the three basic blocking factors, right? Because remember, if we want to have 8 blocks, then it is going to be 8 is nothing but 2 to the power of 3. So log 2, 2 to the power of 3 is 3. So you have to have 3 basic blocking factors. Now these 3 will interact, as you have seen here. You can see it will generate ABCD. If you take these 3 and you multiply, you will get ABCD. If you take this ABCD and you multiply it with AB, you will get CD. You can also get the same CD by taking AC and AD and multiplying, you will get CD. If you take AB and AC, you multiply, you will get BC. And if you take AB and let's say AD, you multiply them, you will get BD. So one way or the other, you can get these 4 extra blocking factors, and this seems to be good because the interactions that are confounded with the blocks are either second order or it is fourth order. The direct effects are spared. The 3-factor interactions are spared. All right, so that is the nice thing about this design. And these are the 7 interactions that will be confounded by the blocks. Let's say we chose these 3 to be the basic blocking factors, because we need to choose 3. Let's say we chose these 3, thinking, oh, these are high order interactions, so cool, right? This will work for us. So what are the derived blocking factors? That is something we should see. So you will get BC, which works out nice. All right, and then you get AD, which is nice, but then you start getting A, you start getting D. So do this and see. So we have the 3 that we chose, and then BC, AD, A, and D. This is a danger sign. We do not want this to happen. So this choice of basis functions or basis blocking factors is not good. This is much better. So some designs are better than the others. Okay, even though they may share other characteristics to be the same, the choices for our basic blocking factors matter a lot. So the overall takeaways from this are: not all experimental plans are the same. Some may have embedded biases or flaws. And with some careful thinking, we can generate good experimental designs. And computer algorithms are available to handle all of these things. So people have come up with algorithms that wherein you state the number of factors, you state the number of experiments that you want to do, and you state the number of blocks. Then it will create the best possible designs for us. All right, so software is available to do all of these things. So you can write your own codes in MATLAB, and MATLAB may very well have some kind of functions that can help to do all of this, but there are specialized software, for example, something like MODDE. So please Google it and see. That is a software that specializes in design of experiments and in chemometric analysis, etc. So software like that can be quite useful. I used to use this about 20 years ago. I have not used it in the recent past because I usually write things in MATLAB, and I'm not working in the industry. I'm in academia, so I've used less of this. But when I was working in an industrial organization at Mitsubishi Chemicals in Japan, I used to use MODDE quite a bit, and many of my colleagues also used it, right, to plan their chemistry experiments, etc. So that is something that I wanted to share with you. Make sure that the data is not contaminated by biases or other things. Particularly protect the direct effects or lower order interactions from known sources of errors, right? Anything that you know is a potential source of problem, we can handle that by proper experimental design. And for the unknown factors, we know that randomization, right, is the only way we can handle anything that we do not know. So block the known and randomize the unknown. This concludes this video segment. Thank you for your time.